Have you ever stopped to wonder what makes your phone light up or how a satellite knows how to stay in orbit? Well, it's not magic. It's actually an invisible language that powers our entire world. And today, we're going to learn the grammar of that language, circuit theory. Let's dive in. Seriously, just think about that for a second. Everything from the smartwatch on your wrist to the enormous data centers that run the internet. There's this common set of rules, a kind of universal grammar that makes it all work. And by the end of this, you're going to understand the basics of that language. Exactly. Circuit theory isn't just a dusty textbook full of equations. No way. It is the instruction manual for electricity itself. It gives us the components, you can think of those as the words, and the laws, that's the grammar, to put those words together in really powerful ways. It's how we understand the tech we already have, and, even more exciting, it's how we invent the technology of tomorrow. All right, so if we're going to learn this language, we first need to meet its most important characters. These are the three core fundamental components you'll find in pretty much every circuit out there. First up, we have the resistor. Its job is super simple but absolutely critical. It provides resistance. You can think of it like friction, but for electricity. It basically controls how much current can flow through a certain part of a circuit. Without resistors, currents would just run wild and, well, fry everything. Next, let's talk about the capacitor. A capacitor is kind of like a tiny, super fast charging battery. It stores up energy in an electric field and then can release it in a blink of an eye. Its main talent is that it really resists sudden changes in voltage, which makes it perfect for smoothing out power supplies and filtering out unwanted noise from signals. And our third key player is the inductor. At its heart, it's basically just a coil of wire. Now, it also stores energy, but not an electric field like a capacitor. It stores it in a magnetic field that gets created when current flows through it. The inductor's special trick is resisting sudden changes in current. It has this kind of electrical inertia that just wants to keep the current flowing nice and smooth. Okay, I know those components can feel a little abstract, but this right here is where it's all going to click. The absolute best way to get this is to imagine electricity is just water flowing through pipes. So a resistor? That's just a narrow piece of pipe that slows the water down. A capacitor? That's a water bucket that can fill up and then dump all its water out at once. An inductor is like a big, heavy water wheel. It takes some effort to get it spinning, but once it's going, it really wants to keep spinning, and that helps maintain a steady flow. See? Simple. Okay, so now we have our components, our words. Now we need the grammar, the absolute rules that tell us how they all have to behave together. And these rules are built on two incredibly important laws figured out by Gustav Kirchhoff way back in the 1840s. And this quote really says it all. You just can't analyze a circuit without these laws. They are the absolute bedrock of all circuit theory. Everything else, all the really complicated stuff we'll touch on in a minute, is built directly on top of these two beautifully simple principles. So let's break them down. Over on the left, we've got Kirchhoff's current law, or KCL. This one is all about the junctions, or nodes, in a circuit, and it simply says that whatever current flows into a meeting point has to be the same amount that flows out. Just like with plumbing, right? You can't just lose water at an intersection. This whole idea is based on the conservation of charge. Now on the right is Kirchhoff's voltage law, or KVL. This one's about any closed loop. It says if you go on a round trip through a circuit loop, adding up all the voltage boosts from batteries and subtracting all the voltage drops from resistors, you'll always end up back at zero. This law is all about the conservation of energy. So, with our components and Kirchhoff's laws, we can figure out pretty simple circuits. But what about the ridiculously complex circuits inside, say, a computer chip? For that, engineers need a much more powerful toolkit. And this is where that toolkit comes in handy. It's filled with these amazing things called network theorems. They're basically just powerful, proven shortcuts that let engineers simplify incredibly messy circuits into something they can actually solve without having to deal with, dozens of impossible equations all at once. Think of this toolkit as having all these specialized instruments inside. You've got things called Thevenin's theorem, Norton's theorem, and the superposition theorem. Now, the names might sound a little intense, but really, each one is just a super clever way of looking at a big, complicated problem from a much simpler angle. We're not going to open the whole toolbox today, but let's pull out just one of these to see how it works. And this is just a beautiful example of simplification. The superposition theorem lets you tackle a circuit that has multiple power sources. The strategy is pure genius. You just calculate the effect of one source at a time, while you pretend the others are turned off. You solve that much, much simpler problem. Then you turn that source off, turn the next one on, and do it again. Once you've done that for every single source, you just add all those individual results together. It's the classic divide and conquer strategy, and it's brilliant. So we've looked at the building blocks, we've learned the rules, and we've even peeked into the advanced toolkit. But why does any of this really matter? Okay, let's zoom out and connect all this theory to the world we live in every single day. Every single concept we've talked about, from how a capacitor works to how you apply a network theorem, isn't just some abstract idea in a book. It is the literal blueprint that engineers use to design, to build, and to fix the technology that completely defines our modern lives. And I mean, just look at what's been built with it. The smartphone you might be watching this on, the power grid lighting your room, a pacemaker keeping a heart beating, the spacecraft exploring Mars. None of it, not a single bit, would be possible without a deep, hands-on understanding of these fundamental principles. This is the science that makes our world go round. And this brings us to a really cool final idea. See, so far we've mostly talked about analysis, which is looking at a circuit that already exists and figuring out what it does. But the real magic is something called synthesis. That's when an engineer starts with only a goal, a desired response, and has to invent the circuit from scratch to make it happen. This is the truly creative act of using this language to write something the world has never seen before. Which leaves us with this one last thought. We've really only just scratched the surface of this incredibly powerful language today. The people who mastered this language in the past gave us things like computers and the internet. So the real question is, now that we have the tools to understand this hidden language, what new wonders, what incredible technologies, and what amazing solutions will the next generation of engineers and inventors build